So welcome back to another Advanced Higher Chemistry video on Unit 3, and in this video we're going to look at three different techniques that can be used for separating chemicals or purifying chemicals. So the three techniques that you really need to know about for Advanced Higher are solvent extraction, distillation and recrystallization. So we'll get into the first one, solvent extraction. So solvent extraction is mostly a separation technique, and it separates molecules depending on their solubility in different solvents. So remember from higher you learned that like dissolves like, polar dissolves polar, non-polar dissolves non-polar. So some compounds might not be very polar, and so you can get them to dissolve in water. However, if you add in some less polar solvent, the compound will be more soluble in that less polar solvent, and so we'll want to move out of the water into that other solvent. And so we can say that that compound has been extracted from the water into this less polar solvent. Now this only works if the two solvents you're using are immiscible. They don't dissolve in one another. In other words, they form layers. So like oil and water. If two solvents mix, then nothing's going to be extracted from one into the other because they become indistinguishable from one another. So solvent extraction looks a bit like this. That bit of equipment is called a separating funnel, and we'll talk about this in more detail later on. But what you can see is the black dots are representing our compound, and it's dissolved in one solvent in this separating funnel. We add in our second solvent to the top, and you can see that you form layers. Now what you need to do quite carefully is actually shake the layers. So to do that, you'd put a stopper on top and you'd shake it. Now that builds up some gas, you build up some pressure whenever you mix two solvents together. So you would have to then turn it upside down and open that tap at the bottom to let some gas, some pressure out. Then put it back the right way, take the stopper off and leave the two layers to settle out. And when those layers settle out, what will have happened is that compound, which is more soluble in the solvent you added in second, most of that compound will have moved into that layer. Now the tap at the bottom allows you to, if you open it, you can watch that bottom layer empty out and you can keep the top layer, which is what's happening now. It's not a perfect technique. You'll always have some compound remaining in the first layer, and we'll get on to how we deal with that later on. But we have a solution, we add a second solvent that is immiscible, we mix them, leave it to settle, and compound should have moved from one layer into the other. So use a separating funnel, so you need to know that bit of equipment, a separating funnel. And you add your second solvent to the funnel and then you stopper the flask. You mix the solutions and you usually turn it upside down to do the mixing. The reason for this is that pressure builds up and you can use the tap that's normally at the bottom to open and release that pressure. And you get like a hiss when you open that tap because gas will rush out. You then turn it back round so that it's the right way up with the tap at the bottom. You take the stopper off. If you don't leave the stopper on, it's going to take a very, very, very long time for the layers to settle. But if you take the stopper off, they will settle relatively quickly. Then the more dense solvent. So you do need to know about density. Density just means for the same volume, it's heavier. And more dense things always sink below less dense things. So your more dense solvent will be at the bottom, your less dense solvent will float on top. And you can use the tap to empty the more dense solvent out first, then you can empty the second layer out into a different container. Now, solvent extraction, remember in the picture when we did it at the start, we saw that there was some compound went into the new solvent and some compound stayed in the original solvent. That is because solvent extraction involves equilibrium. And that is because compounds have a degree of solubility in many different solvents. So you're not going to get a compound that will 100% transfer from one solvent to another. Some of it will stay behind because it has a solubility in that original solvent. Now, what that sets up is an equilibrium that we call the partition coefficient, K. It's going to be the easiest equilibrium constant you've ever worked with, because this partition coefficient is the concentration of solvent that ends up in your one solvent divided by the concentration that ended up in the original solvent. So solvent A in this case is the solvent we add, solvent B is the solvent we started with, confusingly. It always has a value between 0 and 1. The bigger it is, it means a bigger K, so closer to 1, means that the solute is more soluble in A. A K value less than 0.5 or closer to 0 means that it's more soluble in the second solvent. You always want to be using a partition coefficient so that the solvent you want it to go into, the partition coefficient is close to 1, so that you're going to move it into that solvent. Now, because we have an equilibrium, we can actually exploit this. So here we've got an example, and this example, if you're from Glenafur, is in your summary notes for Unit 3. So we're treating solvent A is water, solvent B is hexane, and our K is 0.6. And we've started with 1 mole of solute in hexane. Okay, so our partition coefficient is 0.6. That means that for their 1 mole of solvent, 0.6 of it will end up in water, 0.4 will stay in the hexane. So in our first extraction, we will get 0.6 moles going into water and 0.4 moles staying in the hexane layer. So if we consider everything that we've extracted in the first extraction, we've extracted 0.6 moles. Now if we take that hexane layer and we extract it again with water, now this time we start with 0.4 moles of hexane in it. Now because of the equilibrium constant, we know that 60%, 0.6, of what we started with goes into the water layer. So this time that's 0.24 moles of that 0.4 get extracted and 0.16 remain. If we add up the total amount we've extracted, we've now got 0.84. Now we can do it again, take our hexane layer that contains 0.16 moles and extract it. We end up with 0.096 moles going into the water because it's 60% and 0.064 remaining. We add that together, we've now got a total of 0.94 moles from our starting with 1 mole. So we've nearly extracted it all by doing 3 extractions back to back. Whereas if we'd just done 1, we would have ended up with 0.6. So this is exploiting the fact that equilibrium always means that you get this separation. No matter how little you have, some of it's always going to go into the second solvent based on equilibrium. Now, for the fact that an equilibrium is always set up, it means that we always do extractions a minimum of 3 times. Some people will do it 5 times, but a minimum of 3 should get you close or above 90% of complete extraction. In that experiment, we extracted 3 times with water. Each time was with brand new fresh water, and those 3 extractions get combined together, and in order to end up with our purified compound, you have to evaporate off the solvent. So you just evaporate it off. You can leave it to slowly evaporate at room temperature, or you could evaporate it off using heat. Now, when it comes to choosing an extraction solvent, there are some things that you need to consider. The first thing is that it needs to not be soluble in your starting solvent. So they need to be immiscible. They need to form layers. The second thing is that you always want to make sure that the thing that you are wanting to extract is more soluble in the solvent you're choosing than the solvent it's starting with. Otherwise, it's not really worth your while doing the extraction. So the thing that you want to extract needs to be more soluble in the solvent you're doing the extraction with. The third thing is that at the end, remember, you're needing to evaporate off the solvent. So you need a solvent that is volatile, and that just means has a low enough boiling point that you can evaporate it off. You do not want to spend the majority of your time having to really spend energy and time removing solvent. So you want a solvent that is relatively volatile. And finally, the solvent you choose, it must not react with your compound. So some solvents will react with certain chemicals, so you just need to make sure that a reaction is not going to happen. Our second technique is distillation. Now, distillation separates or purifies compounds based on their boiling points. Your compounds are boiled to cause them to evaporate, and then there is a condenser which turns it back into a liquid, but turns it into a liquid separated in space so that you can collect it in a second container. There are 2 types of distillation. Simple distillation, which is a purifying technique and also a way of testing purity, and fractional distillation, which is a separation technique. So simple distillation looks like this. You have a flask. The green flask is what you start with. It's a round bottom flask, so you're going to heat it up. It's connected through quick fit apparatus to a condenser, and there's also a thermometer which is positioned at the mouth of the condenser so that you can measure the temperature of the gas before it enters the condenser. After the condenser, you've got a receiving flask that's just going to collect any liquid that has condensed. Now, what simple distillation is used for is to separate out the most volatile compound from a mixture. The most volatile means the one with the lowest boiling point. So as I said, you're going to heat your mixture in a round bottom flask. Your desired compound, because it has the lowest boiling point, will boil first. It will reach the condenser, turn into a liquid, and then you can collect it in the second chamber. A thermometer records the temperature of the gas as it enters the condenser. If your compound, if that gas that's evaporated or boiled, is pure, the temperature of that gas as it enters the condenser should equal the boiling point of your compound. So that's one way to check purity. Fractional distillation looks very similar, except what you've got is a fractioning column, which is essentially another condenser, which is situated before the thermometer. So you've got 2 condensers, one positioned upright in what we would call the reflux position, and then everything else looks the same as the normal distillation. Now, fractional distillation is used to separate mixtures of volatile compounds. So volatile just means low boiling point. You heat your mixture in the round bottom flask. This long column, it can be a column or it can be a condenser, is above the flask. It will allow the more volatile substances to pass through, and ones that are less volatile will condense back into the flask. Now, as time goes on, different compounds will pass through this condenser, this long column, at different times, depending on what temperature the flask has reached. and it being a condenser actually really makes the time needed for a gas to pass through it get longer, which allows you to separate things better. And what this allows you to do is collect each compound after it condenses. And you can use the thermometer to check the temperature of the gas as it's entering the condenser so that you could tell what compound it is. What you need to make sure you're doing is changing the collecting flask so that you're capturing each fraction of your distillation, which is allowing you to separate the compounds from one another. There's no point going to the bother of separating them in the fractional distillation equipment if you're going to collect them all in the same flask. You need to make sure that you change it. Now, fractional distillation is used for a lot of really important purposes. One of the most important ones is actually separating different gases from liquid air. So how we get nitrogen, for example, is oxygen and some really rare gases like helium, argon, etc. is by cooling down air so it actually condenses into a liquid, and then doing fractional distillation that allows us to separate the gases based on their boiling points. Another use is separating different fractions of crude oil. So crude oil contains everything from like tar through normal oil, petrol, gasoline, all the way up to natural gas. And by separating it out, it means that we can separate the crude oil out and use it for different purposes. And it's also used for purifying solvents. Now, distillation can also be used to check purity, and I've sort of talked about this previously in the video. So remember, every compound has a unique boiling point. If a compound is pure, its boiling point will be exact. So if you want to test purity, you put what you think is your pure compound into a simple distillation apparatus. If it distills only at the known boiling point, you can say it's pure. If it distills over a range of boiling points, it is impure. You can also use distillation to help identify compounds, because if you can match the temperature at which it boils, at which it's entering the condenser in a distillation experiment, and you know what compounds were in the mixture, you can say, well, that compound has that boiling point, therefore that is the compound that I have extracted. So you can match boiling points to the known boiling points of chemicals. So I know this video is very long. We're going to go into our final technique, which is very, very short, and it's called recrystallization. Recrystallization is used for purifying solids that you've obtained at the end. So you've done your reaction, you've got a solid. The issue can be that that solid might have some unreacted reactants as part of it. So recrystallization allows you to purify it. So what you do is you dissolve your impure solid in the minimum amount of hot solvent. Now it's really important the solvent is hot to start with. And so you're making a hot solution and you need to filter it immediately because you want to filter it while it's still hot. Now anything that doesn't dissolve in that hot solvent is an impurity, so it will be left behind on the filter paper or on the Buchner funnel, and you will then want your filtrate, and you will cool that filtrate down, and your compound will slowly form crystals. It might not look like crystals, but we call it crystallization. They will start to form, but you'll still have some solvent left behind, and anything that's not your compound, that's not pure, will remain in that solvent, your soluble impurities. You can then filter the crystals, wash them. Washing them just means pour a little bit of cold solvent over them while they're still on either your filter funnel or your Buchner funnel, and drying the crystals can mean leaving them on the Buchner funnel, or it can mean putting them in an oven or leaving them in a desiccator. And then you've got your pure compound, and you can test its boiling point, its melting point, etc. Choosing your solvent for this, there's really only two requirements. Your compound must be completely soluble in your solvent at high temperature, but it must not be very soluble at low temperature. So you could be given a list of solvents, told the solubility of your compound at different temperatures, and asked which solvent is the most appropriate. One where it's very soluble at high temperature, but very low solubility at low temperature. That's how you can guarantee it dissolves in a very small amount of solvent, and that it will crystallize as the temperature drops. The last thing is just to know where recrystallization is used. And it's used every day for really important purposes. So it's purifying pharmaceuticals, purifying fertilizers. Fertilizers and pharmaceuticals, probably the two most important things for keeping humans alive in terms of chemistry. But also, if you're making a transition metal complex, you often need to purify it to remove any unreacted ligands or unreacted metal, and also purifying salt from rock salt, which obviously that's where we get salt from. We get it from salt in the ocean, which we need to purify if we're going to use it. So I know that video has gone over the 20-minute mark, but it did cover 3 important techniques used for separating and purifying chemicals.